Good afternoon. Today we are to find the solution to a first order constant coefficient ODE. So the question is, show that the linear differential equation y derivative to be equal to ay plus b, with a not to be equal to 0, b constant, has infinitely many solutions. So the solution y of t is equal to c expo at minus a over b, where the c belongs to real numbers. B over. Good. So from here, solution. We have to first bring or write our ODE, which is y derivative is equal to ay plus b. And we want to show that this ODE has infinite many solutions of this form. So what must we do? So here we have the conventional way and the modern way of solving ODEs. For me, I will employ the modern ways of solving the ODEs. So let's solve this one. First, to use some of the modern techniques, you write the y derivative to be equal to, I want to factor a out from the right hand side. So I'll get a into bracket y plus b over a. From here, I can see that from the left hand side I have y derivative, but the right hand side there is y plus b over a. Then therefore I can modify this one to be of this form, y plus b over a, so that when I find the derivative, it is the same as y derivative. Remember that the b and a are constant. From here, they are constant. So when I find y plus b, all derivative, I will get y derivative. The derivative of b over a will be 0. So from here, I can add b, the fraction b over a, to the left hand side. Y plus b over a, all derivative is equal to a plus b over a. From here, I want to integrate, but the left hand side I have y plus a over b derivative, then the right hand side y plus b over a without derivative. Then I can group the expression involving y on one side. So here I want to divide through by y plus b over a, y plus b over a, so that this one will cancel this one. Leaving, let's come here, y plus b over a derivative over y plus b over a is equal to a. From here, clearly, we can see a certain property being depicted here. We can see that if this entire expression is, let's say, m, it will be m derivative over m. I want to employ a technique of integrate and differentiate. So I can replace this one in the same, I can replace this one by the ln of m all derivative. Are you following? So this expression is the same as this one. I haven't changed anything. So I can do the same thing to this one. So that I can rewrite this one as y plus b over a, the ln of this one, derivative. When you differentiate this one, it will be y plus b over a derivative divided by the function itself. So y plus b over a. I haven't done anything to this one. So when you differentiate this one, it will take you back to this place. And it is equal to, from here, I have a constant. A is a constant. But A can never assume 0. So I want to modify this one too. I can say that A is the same as AT derivative. And it will take me back to the A. We haven't done anything. So here too I can say that A derivative to replace the A. From here, since this one, the one on the left hand side is having derivative and this one is having derivative, don't forget that if you have the derivative of 2x plus x squared, you can say that it is the same as 2x derivative plus x squared derivative. So we can employ the same idea here so that we can bring everything to the left hand side and find one total derivative of it. So you can write this one as the ln, the ln of y plus b on a minus at all derivatives equal to 0. And this one is known as total derivative. Total derivative. And this entire thing is called the total derivative. By the expression psi of ty is equal to ln of b over a minus at is called potential function. So assuming we are asked to find the potential function, then after writing the total derivative, you pick the function inside the derivative. Then you say that let the psi of ty to be equal to that function. That function is called the potential function. But our task here is to find the solution. So from here, since the psi is the same as the expression inside this one, we can rewrite this one as the psi of ty derivative is equal to 0. I want to get rid of the psi. What must we do? We must apply integration here. So we will integrate both sides with respect to t. With respect to t. Because of the derivative, we want to integrate both sides to get rid of the derivative. So you apply the integral sign on both sides, but with respect to what? T. So from here, we will get the psi of t y to be equal to the integral of a constant is c naught, which is the 0, c naught. But we know that this one is the same as the potential function. So wherever we see the psi of ty, we can put the potential function, which is the ln of y plus b over a minus 80 to be equal to C naught, because this one is the same as the psi of Cy. From here, we are looking for the y, the solution y. So we have to maintain the expression containing y on this side and let this one close. So you get the ln of y plus b over a. Let me clean this portion. Is equal to this one crossing to be positive 80 plus C naught. I have the y inside the lane function there, natural logarithm. So I'll apply the exponential function on both sides, so that I'll get y plus b over a to be equal to e expo at times e expo C naught. From here, clearly we can see that the e is a constant and the C naught is a constant. So we can say that let capital C to be equal to e expo C naught. Now we will get y plus b over a to be equal to a expo 80, but C is equal to e expo C naught. So when this one multiply this one, you will get C. Are you following? Good. So from here, we can make y the subject. So y, which is y of t, or y is a function of t, is equal to C e expo 80 minus this one crossing the equal sign over this one. So, sorry, expo 80, yeah, that's the correct thing. C expo 80, yeah. So from here, when you make y the subject, this term will cross to that other side, being negative, as required. So now we've shown that if the first order differential equation y derivative is equal to ay plus b has this solution, indeed, when you solve it, you will get the solution as it has been given. So we've now prove it. Thank you. Kindly subscribe to my channel.